Hello everyone, I am Zhao Xin, the first author of the paper Visible Watermark Removal with Dynamic Kernel and Semantic Aware Propagation. I will introduce this work to you in this video. As a prevalent information carrier nowadays, images are ubiquitous in a wide range of applications, during which the copyright issue becomes critical for information security. To solve this problem, we can superimpose visible watermarks on images to clarify and protect the copyright. As an inverse process, visible watermark removal aims to erase the visible watermark and reconstruct the background image. The figure in this page shows the process of watermark addition and the segmentation results of watermarked images, which will be used in the semantic-aware propagation module introduced in the next. In our work, a novel visible watermark removal method called DKSP is developed, which is equipped with dynamic kernel and semantic-aware propagation. Following previous works, we adopt a multitask learning framework to cope with two tasks: watermark localization and background restoration. One encoder is shared by two tasks, and two decoders are employed for two tasks separately. Specifically, the mask decoder produces watermark masks of different scales, and the background decoder takes these predicted watermark masks as auxiliary information. Previous watermark removal methods often fail to handle diverse watermarks and complicated semantics, which motivates us to make two contributions under this multitask learning framework. On one hand, considering that the watermarks have a diversity of colors, shapes, and patterns, we adapted the network to different types of watermarks using dynamic convolutional filter. Specifically, we design a dynamic kernel module to dynamically generate the convolutional kernel according to the watermark feature, so that the network can adaptively cope with different types of watermarks. We insert dynamic kernel module to both decoders. On the other hand, we explore incorporating semantic information into the network, which has never been studied in the field of watermark removal. When using pre-trained segmentation module to segment a watermarked image, we observe that the segmentation model usually ignores the watermark region or classifies the watermark region as an isolated object. In either case, it is useful to transfer information from semantically similar pixels in the neighboring region to the watermarked pixels. To this end, we develop a semantic-aware propagation module, which is inserted into the background decoder. Next, we will introduce two modules' details. For dynamic kernel module, we will first introduce its application in the mask decoder. Given the feature map produced by the last decoder block, we first produce a rough mask using convolutional layers and sigmoid function. Then using this rough mask, we can get the feature of the watermark region using an element-wise multiplication between the rough mask and the feature map produced by the last decoder block. Then an average pooling and a conv layer are used to generate the dynamic convolutional kernel, which depends on each input watermarked image. Finally, we use the kernel to do the depth-wise conv on the original feature map to get the residual feature map, which is added to a previous produced feature map, which is illustrated as the green feature map in the figure. The summed feature map is used to produce a refined mask. The dynamic kernel module is also used in the last block in background decoder. However, unlike the mask decoder, we directly use the refined mask from mask decoder. Similar to mask decoder, we apply the generated dynamic kernel to obtain a residual feature map. Then we add up residual feature map and original last feature map to get a refined feature map. Finally, refined feature map is delivered to a convolutional layer to generate the background image. Although previous work has also tried to adapt the network according to specific watermark, it simply concatenates watermark feature with the original feature map. In contrast, we generate a watermark-specific dynamic kernel to modulate the feature map more effectively. The watermarked region restored by previous watermark removal methods are often of low quality. For example, blurring distortion artifacts. We conjecture that propagating information from semantically similar neighboring pixels can help recover the watermarked region. For instance, if a part of zebra is covered by a watermark, we can borrow information from the remaining part of Zebra to restore the texture and color of the watermarked region. Therefore, we propose a semantic-aware propagation module and insert it into the background decoder. For details, we first use the off-the-shelf segmentation module to produce the semantic features of the watermarked images. Then we downscale the semantic feature and then use the semantic feature to calculate the cosine similarity between each two pixels, which is called semantic similarity map. The other similarity map is spatial similarity map, which is negatively correlated with the L2 distance between pixels. The two similarities multiplication is the total similarity, which is used to do a matrix multiplication with the flattened input feature map of the module. The result is concatenated with the input feature map as the output of the module. We use two datasets, colored large-scale watermark dataset and Logo30K dataset. Both datasets contain colored watermarks and backgrounds, which are realistic and challenging. In terms of evaluation metrics, we use peak signal to noise ratio, weighted root mean square distance for the restored background image. We use intersection over union and F1 score for the predicted watermark masks. For experiment results, we list the results of our DKSP method and baseline methods in the table. One observation is that watermark removal methods and image content removal methods perform much better than the image-to-image translation methods, which demonstrates the necessity of predicting watermark masks for watermark removal. In addition, baselines WDNet, BVMR, SplitNet, and SLBR, which are specifically designed for watermark removal, outperform other methods in the wider scope. Our DKSP method beats all baseline methods, indicating the advantage of our designed modules. From the table, we can see that methods which can predict more accurate watermark masks tend to generate better background image, which again indicates the importance of mask prediction in watermark removal task. We perform ablation studies on Logo30K dataset to validate the necessity of each component in our method. At the start, we discard the dynamic kernel module and the semantic-aware propagation module. In this case, we obtain a basic network with one common encoder and two separate decoders for two tasks. The obtained results are listed in row 1 in the table. Based on row 1, we add our dynamic kernel module in two decoders, leading to the results in row 5. We can say that our DKM brings notable improvements for both mask prediction and background reconstruction, which verifies the advantage of our proposed DKM. Then we add our semantic-aware propagation module based on row 5, leading to the results on row 9. The promotion demonstrates the effectiveness of our proposed SPM. For qualitative comparison, we show the reconstructed background images in the figure. In each row, we exhibit the watermarked image, the original background image, and the background images recovered using various approaches. Based on the figure, our method is able to recover the texture details and overall structure more accurately and coherently. For example, in the first two rows, the baseline method struggles with removing the watermark color and recovering the background color, while our method is capable of removing the holistic watermark and restoring the texture and color of the background image better. We also visualize the predicted watermark masks from our method and baselines. From the figure, it can be observed that our mask decoder branch can predict the watermark mask more accurately, whereas the baselines are prone to have more missed detection and false alarms. For example, in the first and third rows, our predicted masks are closer to ground truth, whereas the predicted masks from the baseline methods are blurry or incomplete. In the fourth row, the baseline methods may include an extra region mistakenly or miss a large region, whereas our method can precisely localize the watermark in most cases. In this work, we can concentrate on watermark removal and develop a U-Net-like model that incorporates a novel dynamic kernel module and semantic-aware propagation module, which can simultaneously predict watermark masks and reconstruct watermark-free images. The dynamic kernel module can make our network better adapted to watermarks of different shapes, patterns, and colors, while the semantic-aware propagation module can make the restoration of the watermark region more accurate. We conduct comprehensive results on two datasets, which indicates that our approach performs more favorably than the existing approaches. That's all. Thanks for your watching.